This is Unit 7. We're on page 9. This next idea is efficiency. So when we input energy into a machine, we cannot ever have all of that energy appear as useful output. It's not all going to be useful output, or in other words, work. When we input 10,000 joules of gasoline energy into our car, we will not be able to increase the kinetic energy of our car by 10,000 joules. A lot of the input energy becomes heat energy. A lot of it does. So, question mark, what is the percent? What percent is wasted as heat to the engine? If you look at page 13, you can find this in here. Let's see here. Very top. What percent is wasted as heat energy? Very top, and it says 67%. Most of this is heat energy lost, and this is because of friction. It's also between the road and the tires. It could be between the road and the air. There's lots of factors here. When we eat 10,000 joules of energy for lunch, we can't expect it to do 10,000 joules of work using that input. A lot of the input energy or food is used to run our body functions, such as respiration, breathing, heartbeat. Again, a lot of the input becomes heat energy. Efficiency is the measure of how the output compares to the input, and it can be measured as a percentage. Efficiency equals the output or work divided by the input times 100%. Here's an idea. No machine is 100% efficient. It's impossible to build a perpetual motion machine. There's lots of ideas out there of people who think that they have a perpetual motion machine, but none of them work because nothing is 100% efficient. So number one, find the efficiency of an engine that can lift a 60 kilogram box to a height of 12 meters using 20,000 joules of gasoline energy. And so let's start with our efficiency formula. So output divided by input. This will give us a decimal, and at the very end, we'll make it a percentage. For now, we'll just leave it as output divided by input. So the output is work, and the input is just the input, which we are given in this one. So we are lifting this box. Lifting implies a change in potential energy. There's very little potential energy near the floor. There's a lot of potential energy 12 meters up in the air. If you fall from 12 meters, that's a lot of potential energy, the energy that is going to hurt when you hit the ground. Change in potential energy divided by the input. In other words, the mass times the acceleration of gravity times the height divided by the input. A lot of this is setup, just getting in the right mindset. I know a lot of us in the problems want to go right to, here's the exact formula I want, I'm going to plug in the numbers. But sometimes it's going to take some thought. So how am I going to do the output? How am I going to do the input? And so this is just a planning thing. Sometimes things take planning. We know the mass. We know gravity's acceleration. We know the height. And we know the input is 20,000 joules. And so everything here on top, we end up with 72 joules, and on bottom, 70. 7,200 joules and 20,000. So we end up with, this is joules also. Joules divided by joules. So there are no units here. This comes out to be 0.36 in the calculator. That is 36%. And it's an efficiency percentage, so there's not going to be units left over. It's just percent. This engine is 36% efficient. That's pretty good. That's a little bit better than a car, really, because the car was 67% was lost, and so it was 33% efficient. So, example 2, 10,000 joules of gasoline energy are put into each of two engines, A and B. Engine A can lift a 40 kilogram box 10 meters into the air in 8 seconds. Engine B can exert a 200 Newton force while moving an object 30 meters in 20 seconds. Find the efficiency and the power of each engine. I'm going to set this up as a table. Work, efficiency, which is output over input, and power. Which is work divided by time. So it didn't really ask us for work, but you can see that we're going to need it because output is work and power requires work. So object A and object B, and I'm going to go ahead and separate that. So I'm going to go through just engine A first, and we'll keep it all together. So engine A can lift a 40 kilogram box 10 meters through the air in 8 seconds. Lifting. We're talking about change in potential energy. Which is mass times the acceleration of gravity times the height. So the work is, let's see, the mass is 40. Acceleration of gravity, and the height is 10 meters. And so the work is 4,000 joules. Let's take a look at the efficiency. So it's output over input. The output is the work, 4,000 joules. And we're given the input, 10,000 joules. And you really don't even need a calculator for this one. Really, it's 4 over 10. And let's make that a percentage. 40% efficient. 40% efficient is not that bad. Better than the car, better than the engine in example 1, so it's all right. And then the power. Power is the work divided by the time. We know the work is 4,000 joules. We know that it takes 8 seconds. And so this is 500. And joules divided by seconds, joules per second, that's a watt. Engine B can exert a force of 200 newtons while moving an object 30 meters in 20 seconds. We have a force, we have a distance. So we're going to calculate work like this. Force is 200 newtons. Distance is 30 meters. $6,000 joules of work. So the output for the efficiency, the output is 6,000 and the input is the same, it's 10,000 joules. And again, you don't need to put this in your calculator. 6 over 10, that's 6/10, it's 60%. 60% efficiency, that's the best we've seen so far. And the power, so here's our work, 6,000 joules, and it takes 20 seconds. And so we have 300, and a joule per second is a watt, 300 watts. So at the top of the next page, let's evaluate this. Usually a more powerful engine is less efficient. Efficiency does not have to be given as a percentage. So efficiency does not have to be given as a percentage. In reference to the cars that we drive, we can say miles per hour, so that's time, could be a measure of power. Miles per gallon is a measure of efficiency. And usually these two are kind of at odds with each other. A more powerful engine, like let's say a Dodge Challenger, a very powerful engine, not very efficient. If you compared that with something like a Honda Civic, you have less power, more efficient. And so they're indirectly related usually. It's uncommon to have a very powerful car that is very efficient. In reference to a farmer who is plowing a field, we could say acres per hour, because this is amount of work divided by time, that's power. Acres per gallon, so output divided by this is input, and that's a measure of efficiency. As a, quote, engine, the efficiency of the human body is only about 20 or 25% efficient. This means that only about 25% of the energy we eat can be expected to appear as useful output or work. The unit of energy used in biological systems is the calorie. We will define a calorie in the next unit, but we can still work these problems for now. So example 1, how long can a person hike on the energy from 2 quarter pounders, and we have some masses here, and a big Hershey bar if your body is 30% efficient? So the first thing we want to do is look at the amount of energy that we are putting in to our body. So let's see, this quarter pounder's got the hamburger itself, that's the meat, and it's got hamburgers 0.23 kilograms. The bun, 0.1 kilograms. And then the chocolate bar, also 0.1 kilograms. Yes, there are other things on a quarter pounder, ketchup, mustard, pickles, onions, maybe some lettuce, maybe some cheese, but we're ignoring all that other stuff. We're just going to stick with these main components. Excuse me. Looking at the bottom of the page, you can see the calorie content of some various foods here. So we're looking for a hamburger, and so here it is, approximately 4,000 calories per kilogram. So 1 kilogram on the bottom, 4,000 calories. For a total here of 920. The bun, now we don't have buns per se here, but we do have bread. So 2,600 calories per kilogram. And so for the bun, we're looking at 260 calories. Chocolate, 5,000 calories per kilogram. So there's 500 calories. Total input, we have 1,680 calories. It's a big meal. For most of us in the US, it's actually a small meal, but yeah. Something else to keep in mind, up here I said 2 quarter pounders. We really only calculated it for 1 quarter pounder. This is the input from 1 quarter pounder and a big Hershey bar. Now, if you had 2 quarter pounders, you're talking about a lot more. So remember our efficiency. Oops, that's not right. Output divided by the input. And we're going to solve for the output because that's what we really want to know. We know how efficient the thing is, and we know the input. So the output is the efficiency times the input. Efficiency is 30%, which is really 0.3, and the input 1,680 calories. And so the output here is 504 calories. the page we're looking for is not on the slides, but this is page 14, and it says counting calories. There are some activities here. According to this paper, hiking burns 430 calories per hour. So 504 calories is our output. 430 calories per 1 hour. And this tells us that you could hike for 1.17 hours based on this amount of food input and these numbers. Keep in mind the human body is much more complex than we give it credit for in this example. You have fat storages, which are very high in calorie, and they're very good as a fuel tank in case you don't have food. That's why they're hard to get rid of. It's a lot of chemical energy. It's a lot of basically input that's, if you eat too much input, your body saves it for later. How many kilograms of raw apples would you need to eat to swim for 2 hours if your body is 25% efficient? So we know how long we're going to swim. We know that raw apples have calorie content of 500 calories per kilogram. Again, looking at the page with the activities, we see that swimming burns about 790 calories per hour. So first off, let's figure out how much we're going to burn. 2 hours, 790 kilograms per hour. You're talking about burning a lot of energy. 1,580 calories. So the efficiency, output divided by input, and how much would you need to eat? We're concerned with the input here. Input equals the output divided by the efficiency. So the input equals, the output is how much we're going to burn. And the efficiency is 25%, which means 0.25. Based on this efficiency, 6,320 calories need to be put in. And the question is asking how many kilograms of raw apples. And so we have calories per kilogram as a, 500 calories for every 1 kilogram. You're talking about 12.6 kilograms of raw apples. Do any of you think that you could eat 12.6 kilograms of raw apples? So we're talking usually the mass here includes the core, which we don't eat. 12.6 kilograms, to get the number in pounds, you have to multiply it by 2.2. So you're talking about 25 to 30 pounds of raw apples just to get this amount of calories. Not really feasible. I don't know anybody who could eat that many apples. I suppose it's possible, but unlikely.